Hi, and welcome to the Physics 3 tutor, and here we're going to basically pick up right where we stopped in the last section. I want to work a few more problems with capacitors in series and parallel, but I felt like it was good to go ahead and break it here, give you some time to digest the material from before, have a few problems that are a little more simple, and then here we'll get into some different problems. I don't want to say that these are really a whole lot more complicated, they're just different. Then you may have to do a little bit more thinking to figure out what to do. So the first problem in this section goes like this. A capacitor C1 of 6 microfarads is in series with a capacitor C2, which is 4 microfarads, and a potential difference of 200 volts is applied across these two capacitors in series. All right. Part A, there's three parts to this problem. Part A, what is the equivalent capacitance of this arrangement? Part B, what is the charge on each capacitor? And part C, what is the potential difference across each capacitor? So we want to find what is the equivalent capacitance of this arrangement, what is the charge on each one of these capacitors, and the third part is what is the potential difference, which is the voltage, across each of these capacitors. So, just like I always say, it's important to draw a picture. So we have two capacitors and they're in series. So we have this guy, and there's a voltage source here, V, and that goes here. And so I'm going to draw little bubbles here just to remind you that what we're basically going to be doing, this is connected, but basically what we're going to do is we're going to find an equivalent circuit here first. So looking up at these two in series, we're going to have a different circuit. Now, this value, this capacitor, C sub 1, is 6 microfarads, and then C sub 2 is 4 microfarads. So those are the values, and the voltage is 200 volts. Those are all given to you in the problem. So capacitor, 6 microfarads in series with another capacitor, 4 microfarads. Okay, we did that. Potential difference of 200 is applied across these two in series. Okay, we did that. First part, what is the equivalent capacitance? Well, these are in series. So we learned that for an equivalent capacitor in series, it's just 1 over C1 plus 1 over C2, and that is equal to it's not equal to the equivalent capacitor, it's equal to 1 over the equivalent capacitor. So this is going to be equal to 1 over this capacitance here, 6 times 10 to the minus 6, plus 1 over this capacitor, which is 4 times 10 to the minus 6, because they're both microfarads. And then when we continue on down the line, 1 over the equivalent capacitor is going to be equal to, when we evaluate this in our calculator, 1 over 6 times 10 to the minus 6, you're going to get 1.66 times 10 to the 5 plus, and when we evaluate this in our calculator, it'll be 2.5 times 10 to the positive 5. So we can add these two guys together. So 1 over equivalent capacitor, when we add them together, we'll get 4.16 times 10 to the 5. Now that's not the answer because that's equal to 1 over the equivalent capacitance. In order to find the equivalent capacitance, we take this number and we say 1 divided by this number, because we do 1 divided by this, that's going to make equivalent capacitance pop up by itself. On the right hand side we have to say 1 over this. So we'll say 1 over 4.16 times 10 to the 5, which is equal to 2.4 times 10 to the minus 6 farads. And of course, we don't like to leave things in farads. We write it as 2.4 microfarads. All right, so we did that, 2.4 microfarads. Part A is complete. We have two capacitors. We have them in series. We go through the math, which is pretty simple here. We calculate an equivalent capacitance. Now, how do we find the charge Q stored on these capacitors? Now, one thing you have to remember is the charge Q is going to be the same that's stored in both of these. Whenever the capacitors in series, we talked about that, the charge is actually stored and each one of them is exactly the same. There's a couple of different ways to go about doing this. Let's go ahead and tackle the way I think is probably the best. The charge stored on that first capacitor is its capacitance multiplied by V sub 1. And the charge that's on that second capacitor, which is exactly the same because they're both Q, I'm not labeling them Q1 and Q2, they're the same. That's equal to C sub 2 times V sub 2, the second capacitance value times the voltage. The voltage across each of these capacitors is different, but the sum of these voltages must be 200 volts. Okay, so what do we do next? Now, the next thing we're going to do is use the fact that we know that 200 volts must be equal to V1 plus V2, the voltage across capacitor 1 plus the voltage across capacitor 2, because I told you when they're in series like this, the total voltage across the arrangement, these guys must sum up to that because you've got them both placed across the terminals of the battery there. So we write it as this: 200 volts is equal to V1 plus V2, but I know what V1 and V2 are. I can write that as Q divided by C1 plus Q divided by C2, just using these relations. V1 is Q divided by C1, and this one's Q divided by C sub 2. So cutting to the chase here, we have 200 is equal to, I can factor out this Q, 1 over C1 plus 1 over C2. All right? And then what I'm actually trying to find is what is the charge stored. So I'm going to solve for Q. So Q is equal to 200 divided by 1 over C1 plus 1 over C2. And so that's going to be equal to 200 divided by, what is 1 over C1? 1 over C1, C1 is 6 microfarads, so it's going to be 1 over 6 times 10 to the minus 6 plus 1 over, second capacitor is 4 microfarads, so it's 4 times 10 to the minus 6. So that's the answer. I mean, we've calculated the answer. Now you just have to do the math in your calculator. And so what you're going to have when you take 1 over 6 times 10 to the minus 6, 1 over 4 times 10 to the minus 6, you add those two numbers, you take 200 divided by that, and then what you have is 0.48 millicoulombs when you actually convert it back into coulombs and use a nice metric prefix. So there's a couple of ways to really think about this. Notice really what we've done here is I've taken you through a different path, but what we've done is we've taken the voltage, the total voltage across this arrangement, and we've divided it effectively by the equivalent capacitance of this arrangement, basically is what we've sort of done here. And that's just a different way to think about it. So taking it this way I think is a little bit more concrete because you know that the charge on the first capacitor is given by this, the charge in the second capacitor is given by that. The total voltage has to be the sum, and this is the critical thing that you have to know, the intuition I told you that sometimes you have to use in order to be able to proceed with a problem. And this is the intuition that you need here. The total voltage across these capacitors has to be the same as the voltage across each one added together. And that's just because of the way circuits are. I'm trying to teach you that here as we go. Using this fact and using these facts up here, we can rewrite it and basically solve for Q because we know what the capacitors are and we know what the voltages are. Okay, and what you're basically going to get in the answer here, I guess I should have made it a little bit more clear, is you're going to get 4.8 times 10 to the minus 4, and that's coulombs. 4.8 times 10 to the minus 4. So I just chose to move the decimal point one place this way and make it millicoulombs, just because we like to use milli and micro instead of random metric prefixes. Okay, what do we want to do for the third one? The third part says what is the potential difference across each capacitor? In other words, what is the voltage across these capacitors? It's pretty simple to calculate because now we know that Q is equal to C1 times V1, so the charge is equal to the capacitance times the voltage. So the voltage 1 is going to be equal to Q divided by C1. Well, we know what the charge is. We just calculated that. So the charge is 4.8 times 10 to the minus 4 coulombs. The capacitance for that first capacitor is 6 microfarads, so 6 times 10 to the minus 6. So the voltage that's across the first capacitor, if you put a voltmeter up there and measured it, is going to be 80. And that's always defaults to volts. So that's V1. And you do exactly the same thing here. Q is equal to C2 times V2. And you say, all right, well, the voltage, what I'm seeking, is equal to the charge in the capacitor divided by the capacitance. The charge in that capacitor is the same as the other capacitor because they're in series, 4.8 times 10 to the minus 4, divided by, and C sub 2 is the value of the second capacitor, which is 4 microfarads. So 4 times 10 minus 6. And when you take and you divide those two things, V2 is equal to 120, and the unit is going to be volts. So the voltage across the first guy, if you put a meter right here and measured it, it would measure 80 volts. And the voltage across the second guy, if you got a voltmeter and put it here, you would measure 120 volts. Now notice the cool thing here. what we're basically saying is, let's take a different color here. What we're basically saying is, if we put a meter here, what we're going to measure between these guys here is 80 volts. And if we put a meter here, what we're going to measure is 120 volts. Now look here, 80 plus 120 is 200. And that's what you should always have. So it's really nothing magical, it's just self-consistent. You see, we use that fact. We use the fact that these have to be equal to this. We used it right here when we said 200 volts has got to be equal to the individual voltage drops added together. So it's no surprise that when we go through the math and find what the voltages are, that we should be able to add them up and satisfy, the equation that we actually used. So that's sort of a neat thing. And if you actually build a circuit, which is really easy to do, go to Radio Shack, get some capacitors, hook them up to a battery, and get a voltmeter. You can measure them, and you'll see that they'll add up to the total voltages of the source. As they should. Okay, let's go and do another problem. This problem is kind of interesting. It says 3 capacitors are in parallel. Each one has a plate area A, capital A, plate area A, and a plate spacing D, which is the distance between the plates. If an equivalent capacitor for this combination also has a plate area of A, what is its plate spacing? What is its plate spacing? So basically we have a stack of 3 capacitors. Stack is really probably not a great description, but they're in parallel, right? So there's going to be an equivalent capacitance involved in that. We can calculate that. And we want to know if all of these capacitors have the same area, then what would the spacing have to be on that other single capacitor to make the equivalent capacitance equal what we had of the ones that were in parallel? Because obviously if it had the same spacing, it wouldn't be equal, because it would have the same capacitance as one of your other guys. So let's draw a picture and things will be a little bit clearer. So here we have a capacitance, we have another one here, and we have another one here. These are in parallel, just like this. And we have some terminals that we're going to look this way. So C1, C2, C3. Now each one of these guys has a spacing of D, right? And a plate area of A. So you remember back to the basic ideas of capacitance in the last section, they have a physical spacing between the plates and its physical plate area. Now, what we're basically saying is, let me go ahead and switch colors here. What we're basically saying is, this entire thing should be able to be replaced with a single capacitor. A mega capacitor, so to speak, so that if I'm also looking this way, this capacitance is the same as my arrangement of 3 that I have here. So it's basically what we've been saying before. And we've also said that the area of this capacitor is A, the same area as the other guys, but what is its plate spacing going to be? So in other words, what is this plate spacing? Let's call it D for now. D is equal to what? All right, so we have some things to do. The first thing that you should notice, though, is that, look, I've got 3 capacitors in parallel. I know I'm going to have to find an equivalent capacitor. So first, write down that equation, all right? Well, because they're in parallel, the equivalent capacitance is just going to be very simple. C1 plus C2 plus C3. You just add them up because they're in parallel like that, all right? And I don't even need to know what the values are. I'm just going to use this for right now. Now remember, for parallel plate capacitors, I'm going to write it over here. For parallel plate capacitors, the capacitance is equal to the permittivity, epsilon naught, multiplied by the area of the plates divided by the distance, the spacing between the plates. That was the physical description of what the capacitance would be equal to. So we can use that fact. So for C1, it's going to be epsilon naught times A divided by D. And these are identical capacitors, so it's basically going to be the same thing. All of these capacitors are the same. They have the same area and the same distance, so it's basically all going to be the same. All right, now let's go back up to purple here. So what we're basically saying here is the equivalent capacitance is equal to 3 times the permittivity times the area divided by D. So this is the equivalent capacitance of this whole thing. Now what we're saying is we have and we pull an equivalent capacitor off the shelf. We want to know what the spacing is between there. So we're going to set this equivalent capacitance equal to this and see what we end up getting. So when we do that, we're going to set this equal to, this is the equivalent capacitance, A divided by D. And we want to set it equal to this capacitor to do the calculation. This capacitor is also parallel plate, so it's going to basically have the same formula, epsilon naught times the area A, because the area A is the same as this area, divided by the distance between. But I don't want to use the letter D. I'm going to change it to the letter S, because if I put the letter D here, I'm going to get confused. And it's going to algebraically look like this distance here is the same as this distance here, which is not what I'm trying to do. I'm trying to calculate what this distance would be, which is going to be different than this spacing here, in order to give me what I want. So I'm going to change the variable so that I don't get confused. All right, and you'll see that epsilon cancels and area cancels. So if I want to solve for this guy, then basically what you're going to have is, this is 1 over S, so I have 3 divided by D is equal to 1 over S. So this means that S, which is the spacing of my plates over there, flip this over, D divided by 3. D divided by 3, and that's the difference. That is the answer. So the plate spacing of this single capacitor must be 3 times smaller, this plate spacing divided by 3, in order to make this equivalent capacitance equal this one over here. So what it's basically telling you is, because this capacitance, this has 3 capacitors, and you're adding them all up to get your equivalent capacitor, the only way that I can pull another capacitor off the shelf that has the same area but yet yield 3 times this capacitance here is if I make the plates really small together. How close together? How close together? 3 times closer together than these. So in other words, I can intensify the capacitance of a capacitor by bringing these plates close together. You want them as close as you can, because when you do that, the distance goes very small and the capacitance goes very big. The reason that the capacitance gets bigger is because you have more electric field in there. Everything's closer, and so you have a more ability to store charge because you have a more intense electric field in there, and that's basically the reason why. So the plate spacing is going to be D divided by 3. All right, let's do another problem. And this one's kind of interesting. It says you have several 2 microfarad capacitors. Each is capable of withstanding 200 volts without breakdown. We'll talk about that in a second. How would you assemble a combination of these capacitors having an equivalent capacitance of 0.4 microfarads such that this arrangement can withstand 1,000 volts? Such that it can withstand 1,000 volts. The arrangement can. A lot of words. Basically, you have a bucket full of capacitors. Each of them is 2 microfarads. Each of these capacitors can withstand 200 volts. What does that mean? It means that, yeah, I can take a capacitor and I can put a voltage across it, and so it'll do its job, but remember, a capacitor only works if there's a separation between the plates there. So I can have a charge buildup on one side, an electric field in the middle, and a charge buildup on the other side. It stores charge like that. But if you put a higher and a higher and a higher voltage on top of a capacitor, then basically what's going to happen is, in the little atoms here, there's atoms in the air or in the material between the plates of the capacitor, and these atoms have protons and electrons just like any atom. And if you continue to put an electric field on this, then what's going to end up happening is, let's say you had an electric field going this way, and you can make it bigger and bigger, maybe you make it 1,000,000 volts, something really huge. So what's going to end up happening is, the proton is going to be pushed this way because it's going to follow the electric field, and the electron is going to be pushed this way because electrons always go opposite of electric field. So this atom is going to tend to be ripped apart. So when you have an electric field, like you might see 20,000 volts or whatever, a potential difference. If you get to a larger and larger potential difference, which leads to large electric field, then all of the atoms in there, they're going to be stretched apart, and eventually there'll become a point at which the electrons actually kind of get ripped out of the atom and they just leave. And then you have breakdown because basically your electrons are freely moving, and so you kind of have a conducting path there, and that's the spark that you see when you shuffle your feet across the carpet and you go to the doorknob and you get real close to it and you almost touch it. Well, the spark actually happens right before you touch it. And that spark happens because you've built up so much extra charge on yourself that when you get close, the electric field gets really, really great, and the air between your finger and the doorknob breaks down because the electric field is between your finger and the door, and it's pulling those air atoms apart. Eventually, it's going to rip some of those electrons out of their little orbitals, and when you have a soup of electrons kind of floating around like that, then it becomes conducting because the electrons are free to move. You see, in plastic, this is kind of an aside, in plastic, the electrons can't move very much. That's why they don't conduct electricity. In metals, the electrons can move very freely. That's why metals conduct electricity. But if you take an electric field and put it to air, and like your finger, and eventually you rip those electrons out, they're free to move, just like inside of a metal. And they can conduct electricity, and that is basically what you're seeing when you look at that spark. Or inside of a neon light, same kind of thing is happening. You have a plasma in there. That's what's called a plasma. When your electrons are floating around freely and around your atoms, it becomes temporarily electrically conducting. So that's a long way of saying, in this problem it says, each of these capacitors can withstand 200 volts. That means if I can put 199 volts on that capacitor and it's going to be okay. But if I go above 200, it's probably going to basically burn up and break down because the spacing between is filled with something, and that something is going to end up being ripped apart by the electric field eventually, and so then the capacitor won't work anymore. And every capacitor, by the way, has a breakdown voltage printed right on there. You got to make sure you don't put it in an application, that it can't be used in. So that's why when you look inside of a TV, you have very large capacitors because the voltages are high in there. When you look in computer chips, you have very small capacitors because you generally have smaller voltages, smaller currents, and everything else, so you can handle it in there. All right, so that's a kind of a lengthy way of explaining something, but it's physics, so I want to teach you as much as I know about this stuff, and so breakdown voltage is really, really important. And plasma physics, the study of plasmas, is a whole entire area of physics that's really interesting too. Okay, so what I'm trying to do is arrange these capacitors. So I want to put them, in a way that I can take these 2 microfarad capacitors and make them into 0.4 microfarad. So if I put them in parallel, like this, maybe I put 5 of them in a row. Well, if each one of them is 2 microfarads, when I put them in parallel, that's not going to work because the equivalent capacitors in parallel is you just add them together. So if I put 2 microfarads, it would be 2 plus 2, and however many I had, 2 plus 2 plus 2 plus 2. There's no way I'm going to get down to 0.4 microfarads. The only way I can is if I put them in, so I must put in series. Right? So I must put them in series. So I must have some arrangement that's going to basically look like this. And I don't know how many I'm going to have, so I'm going to put dot, 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 but I'm going to do it like this because this is the only way that's going to happen. And you can kind of see that when you write your equation. 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. So the more capacitors I add, then when I flip it over again in the end, I'm going to have a denominator in the fraction that's going to basically make the capacitance go down. So when you have things in series for a capacitor, the only way to drive the total capacitance down of that system is to have them in series like this. Because if you look at this, when you solve for C equivalent, it's going to be equal to 1 over C1. Remember, we wrote this before. C2, 1 over C3 plus dot, dot, dot. So the more capacitors I have, yeah, these are fractions here, but the more I have, I'm still going to get a bigger and bigger denominator. And that's going to drive the total capacitance of that arrangement down lower and lower and lower. So, take that away for now. That's the way we need to go, but we need to decide what to do from now. There's really no better way to do this other than just plug in numbers. So let's say we put in, 3 of these capacitors. Let's put 3 of them in there. So 1 over equivalent capacitor is equal to 1 over 2 times 10 to the minus 6 plus 1 over 2 times 10 to the minus 6 plus 1 over 2 times 10 to the minus 6. And when you do these fractions and add them all up, and then after you get that number, you'd say 1 divided by that number to get C equivalent. The equivalent capacitance in this case is 0.66 microfarads. And that's not really far enough low, so we need to add some more capacitors. So if we add 4 capacitors, then what we're going to have is the same kind of thing. So 1 over equivalent capacitance is 1 over 2 times 10 to the minus 6 plus 1 over 2 times 10 to the minus 6 plus 1 over 2 times 10 to the minus 6 plus 1 over 2 times 10 to the minus 6. All right, so you do the same thing. Fraction, 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 add them up, get a number. 1 divided by that number gives me the equivalent capacitance. And in this case, I get 0.5. Notice that I added another capacitor and my total capacitance went down. So let's do it with 5. Try it with 5 capacitors. So in this case, I'll do, just to ease the pain a little bit, I'll say 5 times 1 over 2 times 10 to the minus 6. Same thing as adding them together. I'm just going to multiply by 5 to keep the writing to a minimum. And so once you do this multiplication and do 1 over that number, the equivalent capacitance of this guy is equal to 0.4 microfarads. 0.4 microfarads. So we got that part of it right. So the question says, have an equivalent capacitance of 0.4 microfarads such that this arrangement can withstand a voltage of 1,000 volts. So let's go back up and revisit our drawing. Now we know we don't have 3 capacitors here. We actually know we have 5 capacitors here. Now, if this guy were connected to a 1,000 volt battery, would this make sense? If I had a 1,000 volt battery, I think, I haven't really gotten into this too much, but if each of these capacitors is the same value, if they're the same value, then everything is symmetrical, and that's going to mean that the voltage drop across this is going to be the same as this one, is going to be the same as this one, is going to be the same as this one, is going to be the same as this one, only because those capacitors are exactly the same value. All right, if they're different values, then the voltage drop is going to be different across each one. But because they're the same, the only thing that makes sense is that you're going to have, and because they must all add up to 1,000, 200 volts, 200 volts, 200 volts, 200 volts, 200 volts, because, 2 times 5 is 10, so 200 times 5 is 1,000. So you have 200 volts here, 200 volts here, 200 volts here, 200 volts here, 200 volts here. So when you put them in this arrangement, each capacitor only has 200 volts across it, which is exactly what your problem says. Each capacitor capable of withstanding 200 volts. It says the whole arrangement must be capable of withstanding 1,000, which it will, because when you put them across the entire arrangement, each capacitor is only going to have a fraction of that voltage really placed upon it. All right, so that's the basic big deal there. So you see, it's not a crazy concept. It's just a matter of understanding intuitively what does series and parallel really mean. Okay, we've got one more. Let's go ahead and erase the board and work that one. Okay, the next problem is really pretty neat. It's a problem that is similar to a lot of test problems out there that you might see. A 100 picofarad capacitor is charged to 50 volts. Then the battery is disconnected from that capacitor. This capacitor is then put in parallel with a second uncharged capacitor. If the measured potential difference drops to 35 volts across that arrangement, what is the value of the second capacitor? This is a classic setup in physics. They give you something that happens in the beginning, and then they tell you something else happens to that, and you're trying to find out something related to the second little setup over here. The trick is you've got to calculate everything you know about the initial setup, and you're almost certainly going to use one of those things you calculate over in the second setup. So in this case, we know a capacitor is charged to 50 volts. Okay, that's a fact. That's something we can use to calculate something. Then the battery is disconnected. Okay. Then we take that arrangement, connect it to another capacitor, and the voltage drops. And basically we want to find what is the value of the second capacitor. So draw a picture. It's going to help you. So the first part of this thing, the setup, is we have a 50 volt battery, like this, and we connect it across this capacitor, like this. And we know that this is a 100 picofarad capacitor, and we know, just from thinking about everything before, that, I hate doing this and cluttering up my drawing, 50 volts is what we would measure. If we get a voltmeter and put it here, we're going to measure 50 volts because it's directly in parallel with, it's directly connected to the battery terminals. So let's go and say, okay, so we charge it up like this, and then we take it and we do the following thing to it. We disconnect the battery, so now we just simply have the capacitor sitting out here, this 100 picofarad capacitor, and we connect it to another capacitor, right? And then this second capacitor, we do not know the value of, but we measure the voltage right here, and we see that it has dropped 35 volts. Now notice the battery is no longer here at all because we disconnected the battery. So this guy, this capacitor is still the same 100 picofarad. So this is the setup, and we're trying to find C. So we have this battery. It charges this guy up to whatever value that we'll calculate in a second, and then we disconnect it, and then we take another capacitor and we connect it to it like this, and then the voltage goes and goes down because this capacitor begins delivering charge over to this other unknown capacitor, and what we're trying to find is what is the value of this capacitor right here. So this sort of behaves almost like a battery and delivers charge. That's what capacitors do. They store charge and they deliver charge when you discharge them. So what is the value of that capacitor? My advice is always to calculate what you know from here and then see if that knowledge can be carried over. So we know that in this arrangement, without any of that stuff, that the charge that's stored is equal to the capacitance times the voltage. And we know how to calculate this because the capacitance is 100 picofarads, 100 times 10 to the minus 12. Don't forget pico is 10 to the minus 12. The voltage is 50. So the charge that's stored on this capacitor is 5 times 10 to the minus 9 coulombs. This is the charge stored in this capacitor. You know, we hook the battery up, we leave it there for 10 minutes, and we come back, and this is the charge that we know we can calculate is inside of here. Now, we disconnect the battery. At the moment we disconnect the battery, assuming a perfect capacitor, that charge should stay inside that capacitor basically forever, right? Now, in the real world, they'll slowly leak away through the air, really, but very slowly. You wouldn't really notice it. But in a perfect physics world, this charge that we calculate should be in here. So when we hook it up to this other capacitor, this is going to act as a source of electricity, or a source of charge. So we take this and we use this fact over here. So we measure 35 volts after a certain period of time. So we do the same thing over here. The Q is equal to CV for this capacitor right here. Actually, no, what I want to do here is continue to look at this capacitor. We're going to continue to look at this capacitor after we've already done this hookup stuff here, like this. The charge inside this capacitor is really not known because it's going to bleed charge out. But what we do know is that after a certain period of time, it's 100 picofarads, and the voltage across this capacitor has dropped to 35 volts. Right? Has dropped to 35 volts. So what we can calculate when we do this multiplication is that after a certain period of time, 3.5 times 10 to the minus 9 coulombs stored, I'm going to help you out and write this, stored, if I can write stored properly, stored on first capacitor, this is the first capacitor, the original one, after connected to second capacitor. Okay, and what is this one? Charge initially on first capacitor. So what have we found here? We charge to a certain value of coulombs, we hook it up to another capacitor, and we find out that after a certain period of time, the charge goes down. It goes from 5 times 10 to the minus 9 down to 3.5 times 10 to the 9. So if we take the final value of this charge and subtract the initial value, which is this one, then what we're going to get is 3.5 times 10 to the minus 9 minus 5 times 10 to the minus 9. So QF minus QI is equal to negative 1.5 times 10 to the minus 9. Why is it negative? It's negative because the final value was less than the initial value. So we've actually lost charge from this capacitor, which makes total sense because we think it should if it's delivering charge out. We've lost this many coulombs. So if we've lost this many coulombs from this capacitor, this is the leap of insight you have to have. If we've lost this many coulombs, where did they go? Well, it's only connected to this other capacitor. So every coulomb lost must go straight into this capacitor. So that's sort of the major leap that you have to make in this problem. So I'm going to draw a little line here. Second capacitor gains a positive 1.5 times 10 to the minus 9 coulombs. So we know how much charge that second guy gains, and once we know that, we know it's equal to the capacitance times the voltage there. So the charge is 1.5 times 10 to the negative 9, and that's equal to that capacitance, which we don't know, that's what we're solving for, times the voltage across, but we're given that 35 volts. So the capacitance of that capacitor is 4.3 times 10 to the minus 11 farads, which if you think about it, if you move your decimal this way, then it'll be to the minus 12, so that's 43 picofarads. So this capacitor is 43 picofarads for the second capacitor, which is the one that we were trying to do. It's a really cool problem because it forces you to think about what's happening. You charge this capacitor up, and you can calculate, because of the voltage and the capacitance, how much charge it has. You connect it over here. You know intuitively that it's probably delivering and bleeding charge over here, probably reducing its charge level, so you calculate that. Same capacitance, reduced voltage because of what's happened here, and so the charge stored is now less. The leap of faith you need to, or the leap of insight, is to know that if I subtract these two guys, then that means that this capacitor has lost this much charge. The other capacitor has gained exactly the same amount of charge. Once I know that, I know what the second capacitor's Q is, I know what the second capacitor's voltage is, I can calculate that second capacitor's capacitance, which is what the problem asked us to do. Okay, we're done with this section. We've learned about capacitors in series and how to derive that. We've learned about capacitors in parallel. We've learned how to derive that. We've learned how to simplify capacitor arrangements. We've learned how to calculate simple problems. We're just sort of doing some basic stuff. And we've learned how to apply these things to more complicated problems that you would need to think about. Now notice, the math involved in this is really not hard. You've got basic algebra. I mean, you really have nothing complicated, but physics is not about complicated math usually. It's about knowing what to do. It's about having an insight and sort of working enough problems that you get your brain gets good at figuring out what to do. You have to take it one step at a time. First I can do this, then I can do this. Oh, now I see it. But see, when I first started this problem, I didn't really know how I was going to do it. I didn't have it all mapped out in my head. I had to start somewhere and then incrementally make steps. And then finally you get to the point you're like, I get it. If I set this equal to this, I can do this. But you don't have that in your head ahead of time. You have to work towards it. Everybody's like that. You have to get good at that. So practice your problems. You'll get better at it. We'll continue this journey through electricity and magnetism, learn a lot of really neat stuff. I'm Jason. I hope you've learned something in this section. Keep practicing your problems, and you'll do just fine in your test.